All right, so I'm going to try sharing my screen right now.
Okay, so thank you everybody for joining. Today we have Professor Chris Heckman. Sorry, I lost this add button. Okay, never mind. I people. Thank you so much, Chris, for your time and this presentation. That's going to be really helpful for our students. So I'm recording this session so that for students who cannot attend this, we'll make it available for everybody to listen. Chris, of course, is recruiting for spring 2023, as he's not teaching in fall 2022. So again, once again, thank you so much, Chris, and on to you.
Yep, thanks. So can you hear me okay?
Mm-hmm.
Okay, great. All right, so if anyone has any questions or anything like that, feel free to interrupt, and there will be plenty of time at the end to ask questions too if you just want to hold on. Just going to give you a brief introduction into a few projects that are going on with my group as well as with other robotics groups here. And many of you may actually be taking some classes with some of my colleagues, and so I'll give a short discussion of what's going on with them. So let's get started. Okay, so here's just a broad overview, and I'll talk about a few of these applications today, especially the top three. And as far as the rest of them, I won't be able to go into them, but I wanted to just at least note here that there's more than just field robotics, radar, and neurosymbolic AI that's being evaluated and researched in my group. For instance, we are dealing with a bunch of metric maps and different types of ways robots can make spatial decisions that are more metrically based, like if you're familiar with calculus and algorithms, that might be more familiar to you, as well as some uncertainty quantification, things like using Kalman filters and Gaussian processes and regressing different types of functions that have to do with uncertainty in the real world. And so I won't talk about those today, but I just wanted to give a shout out to them. And finally, the last thing that I wanted to note is that we do actually have a new book with all the colleagues here of mine in robotics. And this book is something that's actually freely available online. It's also in print by MIT Press. It's called Introduction to Autonomous Robots, Mechanisms, Sensors, Actuators, and Algorithms. And the point of that book is really to give you a very gentle, colloquial introduction to the field, but also having rigor in places where you might need it. Honestly, I think that if you're pretty savvy with linear algebra and calculus, reading that book probably takes like a weekend, and that might be something of interest to you. You can just go online and compile it. So I wanted to give you first like this montage. It's a video that was created by one of my undergraduate students of a deployment that we did with some of our experimental robots for the DARPA Subtraining Challenge last year. And you'll see a few things here, like that we actually go out to different sites and people wear hard hats and reflective vests. And, there are actually robots that are moving around in environments that have never been explored by a robot before, at least. This is a mine that was in Idaho Springs. In this case, this is actually one of our test deployments. It's a place where we collected data, refined our algorithms multiple times before participating in the DARPA Subterranean Challenge, which was a large, like $80 million program from DARPA. And, there's a lot of dramatic music in the background that you're not hearing, but essentially we built these robots to autonomously navigate in this space. And the reason why these humans are there, these are PhD students, master's students, that are actually looking at what the robot is doing and trying to evaluate their behavior, see whether or not they're doing what we expect them to. A couple of different.
Video.
Can you hear me still? I can't hear you if you're talking, Rashi.
I can hear you.
Okay, great. So I got a button that said, anyway, someone asked me to unmute, but okay, so these robots are basically using these different sensors, autonomously operating here. We have a couple of different robots that we use for this competition that are still being used for much of the research that we do. We're not as interested just in subterranean tasks. That was a very motivating experience for us for this particular project, but this was actually just one of the many field robotics types of exercises that we do in our group. So like I mentioned, this was actually part of a large competition, and our group does participate in actually like national or international competitions that are usually hosted by sponsoring agencies like DARPA to be able to go and build and deploy these robots. You know, a large part of like 99% of our work is the actual building and development of algorithms that support a particular application. And then the last 1% is actually competing, which is kind of fun. Although, you know, it's always a crapshoot whether a robot will just explode, not literally, but figuratively just fall apart and won't know what to do. And one part, the reason why I'm showing this picture here is because we actually do a lot of human robot interaction work implicitly as a result of the work that we do in my group. So here's a human, we were allowed one human to interface with this whole system. And the system thereby needed to be quite autonomous. And even in places where it was deep underground, we had no comms to the robot, the human had no power over that whatsoever. And now the robots have to work completely autonomously or fail completely autonomously, as the case may be. But, you know, one human was allowed to have interaction with that. And that human interface that you see here it was not a big part of our work. It was actually pretty, you know, built on prior libraries and everything. But the way that we designed the interfacing with the human was something that is in itself a very deep research area, and one that is also explored by Brad Hayes and Alessandro Arcone, two colleagues of mine. So this is just, you know, there are many different facets of robotics. One of them is algorithms, another one is, you know, systems, and finally there's how does a human play with these sorts of autonomous agents. Just to give you an idea, like, you know, this was pretty hard, and I want to show, this is a hard competition. I want to show you why I think it's hard. And one of them is that you have multi-scale types of behaviors that need to be exhibited by robots in these environments. So for instance, you can have very narrow corridors like the one on the right, where there are tracks and there's very fine geometry that has to be planned over and perceived, sensors that have to fuse data in as the robot's moving through this environment and figure out what to do. And the second thing is you actually have to, you know, in this case, navigate in like a large expanse, like on the left, like a cave, figure out where there are small rocks that might be threatening to the robot's locomotion, but also understand whether or not you've done full coverage and seen everything that there is to see in this particular cave. So this is like one kind of algorithmic problem that you could imagine scaling in different ways. And those sorts of algorithms for planning and sensor perception, or the consumption of sensor data into data products that then could be used for navigation or other behavioral systems is actually really like the fundamental work that goes on in our group. Not the building of platforms, not the building of sensors or anything like this, but the algorithms that power perception and decision-making in these environments. And just as another example, like the types of environments we're looking at are not just quote unquote fields, right? They're not just these places where there's some kind of like natural thing to explore, working in a desert or something. They're also urban and built environments. Working in places like subway systems, this was actually part of the course that was built as part of that competition. But you know, operating in buildings that are both in perfectly fine condition, like the engineering center, all the way to like, you know, being on fire, falling apart, disaster recovery. These are places that we're really interested in. And I want to say that like this is kind of an unknown feature of being a roboticist here at Boulder, but we actually are well known for the work that we do in this area. So by that I mean, you know, what I want to point out is that there are a number of teams that you may be familiar with, institutions that came together and, you know, pulled a team together to do this. And you know, we beat many of them. And what's not on this slide here, I guess CoStar is on this slide. CoStar was a collaboration between MIT, Jet Propulsion Lab, and like Berkeley. As the team that was made up Explorer was Carnegie Mellon, and the team that, you know, beat us, two teams that beat us in this competition were in Zurich and Norwegian Technical, as well as CSIRO, which is basically like, you know, a very large research apparatus for the Australian Commonwealth. So this is, you know, we actually did compete well in this competition compared with international peers. And I think that this is a testament not just to, you know, the growth that the robotics area has seen here in the past several years, but also partnerships that have been developed. You'll see here a number of faculty members, not just in our department, but also in the mechanical and aerospace engineering department, and teams coming together from all different you know, walks of their careers, whether it's undergraduates, graduate students, PhD students, faculty, postdocs, all coming together to try to do this work. So things are pretty exciting, I think, for the robotics group. When I talk about, perception, I want to give a little bit of context to that. So we are very interested in my group working with automotive LiDAR, working with cameras, and how we are able to parse camera data using machine learning techniques, especially modern techniques like visual transformers, and contributing constantly to that field. We use, commodity cameras, not just machine vision cameras, but ones that are, cheaper and can be placed everywhere, like these real senses that have onboard vision and depth sensing based on stereo algorithms. We use GPS if we're outdoors, if available, and we use inertial measurement units, and the fusion of all these data together is what provides us some idea of where we are and what we're looking at. And the co-location of these data is actually a very interesting problem from a machine learning perspective too. That is something that we focus on. So one area that is not as well researched in our view is radar. And so I want to talk a little bit about radar here. Radar has been around for a long time. I'm sure many of you know about radar, but millimeter wave radar on a system on a chip that has been fabbed into a sensor, that is actually a very rare sensor. That's something that's only come about in the past 5 years or so. And so that enables us to be able to do perception with these small packages of sensors. So what I just showed you, and I'll if I can show again, is if we are comparing how LiDAR and radar work, what you'll see here is that in this vision, it was just this camera front-facing view, in a completely pristine environment without any fog or obscurance or anything, a LiDAR map can be pretty dense on the surfaces of the environment, which means that you can actually see where you're going and be able to use LiDAR. But in cases where there's heavy obscurance like this fog, then that rainbow colored map just completely washed out the entire scene. And so what we're interested in is trying to solve problems where we can use other sensor modalities such as radar to be able to do mapping and localization in environments like that. And it's not just for environments such as, like in built environments where there's some sort of disaster going on, or some foggy environments like for driving in a foggy day or something, but also places like this where we are trying to, go and check out caves on the moon or in Mars, and you see all this haze, and how far can a LiDAR possibly go here? What does radar mean as an alternative for sensing? I think that's more of a motivational case for us, because then we can actually see, well, these algorithms don't have to just work in places where something has gone wrong, but also just in general supporting autonomy. And if you're on these different environments where there's a lot of obscurance going on, then how do you possibly do mapping here? LiDAR is not going to work. So we're not the only ones who've done this kind of work. Radar has been, a mainstay of some sensing problems since, like I said, 70 years ago. Recently, it's moved into the autonomous driving domain, and many of you may be familiar with, autonomous driving is frequently reliant on a suite of sensors like LiDAR, cameras, and automotive radar, and sometimes that's in these tiny little packages that are used for cruise control and automatic braking. Many modern cars are built with these kinds of things built in. The new way that this is being introduced is actually just as a replacement for LiDAR. And so you'll see here is this rather large, big bulky radar sensor sitting on the top of this autonomous vehicle. And this is essentially the replacement for what would have been a stack of LiDARs. And there are a few advantages to this, like the high density of radar returns. There are drawbacks, like the sensor is tens of thousands of dollars, it weighs many kilograms, and has a high power draw. So even though it runs in the radar spectrum, it sort of has some downsides. These new radar sensors that are being built out, like I mentioned, just directly printed onto a PCB with a chip that is driving the front end of the radar synthesis. That's they're like an order of magnitude lower weight, several orders of magnitude lower weight, and also lower power draw, but also orders of magnitude cheaper. So each one of these sensors is about $300 or so. So we have these sensors. We're trying to figure out what's possible with them. Recently, we've been collecting data, creating data sets for machine learning tools that we're building that are using multiple sensors with the supervisory signal of LiDAR and an IMU and some cameras, multiple different radars, comparing and contrasting them. And something to see is that the data coming out of this can come in many different forms, like in a 2D slice of what this might look like along a range and azimuth sort of image. You'd have maybe like a high intensity return of some object that's sitting over in that like light white area in that image. If I wanted to show a video of this, then that actually can sometimes be helpful. Maybe you can see my cursor, but the white points are LiDAR points that are sitting on both sides of like a tunnel that we're walking through. And the lit up points here are these radar returns. You can see that they're actually pretty high density and overlaying on top of where a LiDAR return comes from. But they're also like presenting some really significant challenges from a signal processing standpoint and also downstream machine learning tasks, which includes that, you know, there are these like ringed bands of returns that even in places where there are no objects, right? And so being able to come up with novel machine learning techniques to be able to reduce the noise in these, work over this very novel, I would say, domain, this range and azimuth domain, rather than like a 2D image domain. That's sort of some of the ideas that you can imagine coming up in the work that we're pursuing. Here you can see just a video of if we walk the sensor forward, then you can see how these radar scans evolve with respect to also how the 3D scan of the environment evolves. This should give you some hope that like radar can work, but also some opportunity when it comes to algorithm development, especially when we develop data sets like this. One last thing is we actually have deployed this on a real robot. Let me see if I can mute the. So this is a quad rotor, and now in this case, it's only being, it's going to only be controlled using this radar inertial rig that we have. That's the fusion of millimeter wave radar from that one sensor, as well as an inertial measurement unit. And it's able to do station keeping. Let me see, okay, there. Station keeping, which is basically just hovering in one place, building a map of its environment, and just trying to sort of like go in a figure 8 in this case around this trajectory. The motion capture cameras, if you're wondering, they're just used here for purely for the purpose of ground truthing our algorithms. So in this case, you know, we're actually able to navigate using this radar inertial rig alone. Some recent work we've done is also focused on the metric side of this. The metric side means like the ability for us to actually extract 3D maps, as well as get state estimation, X, Y, Z, relative yaw, and velocity. And so from that, we were able to go and reconstruct the positions and orientations of the robot and follow navigation systems as a result of it. So here we have this 3D mapping system based purely on the radar returns, and that's those green blocks that are coming up, which correspond with the walls in this corridor that we're walking down. The white little dots are actually places where there are radar returns. So this noise filter that we've created from a point net classifier in this case, which is a 3D convolutional neural network, is rejecting those outliers and then being able to build these dense maps that then correspond with obstacles, things that we should avoid in a control sense. So you can see sort of how all this plays together. One last comment, you know, this is the last project I can talk about today before I take questions. We're not only interested in the metric. In this case, I'm going to talk a little bit about a project that I have with natural language processing collaborators. And this project is motivated by a general like problem of how do we understand videos, images, metadata, and speech and text in a unified framework so that we can actually come up with comparative understandings of or what we call hypotheses of what is going on in a scene. And I want to provide you an example for this. The reason that this image is here is, just as an aside, this is not a robotics problem per se. This is really a multimodal machine learning problem that has robotics implications. And so that's sort of one note about that. Our group sort of works across different fields, not only in this field robotics context. So here's my example for you, and then I'll close with this. Okay, so let's say that I give you this image from a newsreel, and the newsreel says something like, okay, opponents of this president of Turkey rally in a park as the president of Turkey and President Donald Trump at the time in 2017 are meeting at the White House in Washington, D.C. And then there's this image here, right? So what's going on in this piece of information that I've given you, these two pieces of information, in fact, your mind is doing some kind of multimodal alignment of the data. So you've extracted some stuff that's going on in the image, you've extracted what's going on in the caption, and then there's some sort of alignment across some components, right? Not everything in this image corresponds to something in the caption, and vice versa for the caption to the image. So there's some complements and some intersection of data, right? If I were to try to reduce this through a machine learning system of what's going on in an image and what's going on with the text, I'm going to do this in tandem. On the left, I'm going to show you my parsing of what's happening of the text of that caption. And on the right, I'm going to show you my parsing of what's happening in the image. Okay, so first thing that you might do is, drag out the word rally from the caption. That's the event that's occurring. And the rally might have some properties attached to it. That's in the language side. Meanwhile, if I look at the image, I can clearly see that there's some indications of a rally occurring. So like there are people with signs, they're gathered, there's police present. I mean, this might invoke notions of a rally. If you had a really good segmentation system for an image, then it might be able to classify this. It might also just come out as some intermediate vector representation that's representing the knowledge of a rally. Let's put that aside for now. And there's some metadata attached to the image, right? So we can all agree that images have metadata, like when they were captured and maybe even some GPS location. Okay, so in the parsing and the subpars, if you will, of rallies, then you can imagine that there's some real facts associated with rallies. Like they can be for some purposes that are, yeah, go vote for this bill or something. But another property of rallies is that they can be opposing people. It can be a political rally that's in opposition to an idea. And we can see that in the image because there's this thing that says stop. And then there are people with big old signs, and there's clearly some sort of opposition to an idea. So you can see that there is actually like a deeper level of correspondence between the language and the image than what originally meets the eye. We're not just opposing a person. If you had a really, really good image parser, you could see these tiny little pictures of President Erdogan or cartoons of President Erdogan, and then, oh, this person loves ISIS. Like this is negative towards this particular actor on the image side, and on the left side in the language parse, you could say, oh, I'm opposing this president of Turkey, and not just that, I actually have a Wikidata entry for President Erdogan because he's a well-known figure and he has an org role of president of Turkey. Okay, so you can pick up a lot, right, from what is originally just two pieces of information if you start really investigating what's happening. From here, you can maybe pick up also that the rally is occurring at Lafayette Park. That was part of the caption. That's a place. It also has a Wikidata entry. And then on the right, for the image parse, you can say that this is some sort of park, and that combined with GPS coordinates probably means that you're in Lafayette Park. What do you know? Okay, so, and then you can also do it on time, right? The time metadata in the image corresponds with some text metadata on the left. So that is like a full, there's an amazing parse, right? First of all, like if you had a language parsing system that could do this, then you would come up with this graph on the left. These have been developed, different types of transformer techniques in machine learning can actually do graph parses like this, or we actually have tools that are unique to us here at CU called like abstract meaning representation parses, which can do something similar. On the right, we have this segmentation system, and segmentation systems actually have gotten this level of capability. So the ability for us to use, for instance, visual transformers or different types of well-tuned deep convolutional neural networks have been able to get to this level as well. So, what I just said was not science fiction. This is actually being done. Okay, so now here's where things really get interesting. Okay, so let's say that you have that great parse. Now I give you another piece of information, and it says, US President Donald Trump shakes hands with the Turkish president in the Oval Office. Okay, so now we have this piece of information. It's actually happening on the same day. It's taken by a different person. We have two different sources. One source is telling you, this is what is happening. Opponents of President of Turkey Recep Tayyip Erdogan rally in Lafayette Park because a meeting is happening. And then we actually can align that with the second half of that caption, which we did not parse before, remember, because there was nothing that was done in that scene that corresponded with any piece of information from that image. But now we have complementary information from a second image that is providing us more information about what's happening in this scene. So you can start thinking about like the total compendium of information that might be attached to multiple images and multiple text strings, right? And how we can put these together. Now, this is the point, right? There were lots of questions when this was first happening about like, why did, this is actually sometime, this is 5 years ago, so maybe we all forgot, but let me recall for you that what happened at this particular incident was that President Erdogan's security force actually went and like did hand-to-hand combat with these otherwise peaceful demonstrators in this Lafayette Park. And there's another, now I'm going to introduce for you this other piece of information, which is coming from the Turkish media. Okay, Turkish media that is pro-Erdogan. And it says, seeing how few US police officers were acting against the riot of the PKK PYD supporters or the President Erdogan supporters, a group including the president's security details and the Turkish police embassy stepped in. So what is to note here is that this is a complementing and actually contradicting fact, right? I mean, this is a very different perspective of what happened in that park. And so these are two separate hypotheses that can be clustered is the idea. The first one is that the hypothesis one, the order that was given by President Erdogan caused the supporters to be beaten. And the second one was that a lack of opposition from US police caused the police officers from the Turkish embassy to step in. So these are two separate views and they need to be rectified, right? How to rectify them? That's someone else's problem. The fact that these two were clustered in such a way and found to be opposing, that's what's really remarkable. So, the reason why I was giving you this context again is just like this level of understanding of scenes and multiple different information that can be parsed together is one of the things that we are interested in our group, not just from, a general machine learning perspective, but also for the perspective of if I wanted to give a robot an instruction and started giving it multiple pieces of information to do so, then it should be able to parse all of these in order to make a decision. So with that, I am done with my 3 tableaus of projects. And so I'm interested in any questions you might have for, wherever the discussion might take us.
Hello, Professor.
Yeah.
Thank you for the presentation, first of all. My question is regarding the multi-robot communication project. I just wanted to know if the project is still active, or it's done and no work is being.
Yeah, so you're talking about a project that's on my website, not something I talked about today, just for everybody else's context.
Yes.
Yeah. So we absolutely do still do research in multi-robot communication and collaboration. Just to give everyone a flavor of what that is, it's basically the ability for us to have a fleet of robots, in this case, usually like 2, 3, 4, not like an enormous number, but enough that they are all collecting information in different perspectives of a scene, and that they are able to share this information in such a way that they can build their own understanding of what's going on while also, cooperating in that environment. So this is still ongoing. It really was like the purpose of that project was to solve DARPA subtraining challenge type of issues. The reason why it still goes on is because there are a lot of places where robot coordination and multi-robot communication is like completely not understood well, is not performed well. And so that's one of the reasons why I would recommend, we continue doing research in it. I would say that, for the most part, we have a test bed in our lab, like all these different robots that have been built up with a variety of wireless capabilities for communication, multiple modalities for it. So we have an amazing test bed for it. And we have a good place where we've launched off. But it really depends based on the students' interest, probably where that project would go.
Thank you. Actually, I should have mentioned it before. I'm a master's student, and that's why I just wanted to see if there's still a scope of work where I could participate. I should probably take it offline and reach out to the lab to get more update on the project and how I can contribute.
Yeah, I think that so Rajshri had just made a note, like how do students get involved? Great question. So as I mentioned previously, or as Rajshri implied, I'm not teaching this semester, and actually, I'm gonna have another kid in a month. So it's like, that's the reason why I'm not teaching this semester and why I'm not taking new students at this moment. But in the spring, I will. That is not to say that you could not, if you are interested in any project that's going on, you can't do it. It's just that there's going to be very little direction from me, if none at all. But we have 7 PhD students in the group, and they're all very capable at this point of being able to work with you on projects. So I think if you're interested in something that's going on, you should email me, and then I'll connect you with the right student. That's probably the easiest way to do it.
Perfect. Yeah, that helps. Thank you.
Yep, no problem. Other questions?
I have a question.
Yeah, Bill.
Yes, thank you. Yeah, so basically I did the entire Master's of Engineering from 2015 to 2018, and I'm looking to getting back into research. This seems to be a very exciting opportunity. Yeah, so so how would I go about mentioning that in my personal statement, saying like, oh, I want to apply to the PhD program, citing your project is like, yeah, I'm looking at yours and maybe 2 others. They're like, wow, this is something that's more interesting than working for a bank, right?
Yeah, I think that's great. So yeah, thanks for your question. So what I would recommend generally, if you're interested in applying and getting into research or back into research, like personal statements absolutely should mention, if you're interested in a particular project, why you're interested in it, or why you're interested in it, how your background may connect. I wouldn't, I think that there's also, we all know this, like faculty web pages can be out of date, right? And they may not list absolutely current projects. Sometimes it helps to reach out to a faculty member. Sometimes they're unable to answer individual queries because, we can get a lot of queries around application time of what available projects are out there. And also, frankly, the timelines for getting into a particular project, like we accept you in like December and then you don't show up for 9 months. So projects have moved on, right? So it's like, if you have a particular type of interest, then you should let us know. And in particular, also like why you want to get back into this, like I think, or why you want to do research, like that all provides for really good context. The last thing I'll note is we always, all applications get read, right? It's just a matter of like whether we are like, we need to reach out to this person now, or whether we need to reach out to this person later. The one thing that I think is important is like, once you send away an application, you absolutely should reach out to the people you just sent the application to, right? So you said, let's say you listed me, Alessandra, and Brad, you should send an email to each of us and say, hey, I just applied to your department. I just was hoping that, you give my application a look, because, I mentioned you, I like these projects, and, if you're available, then we should meet up and have a Zoom chat for a few minutes. That's normal. And I think that's actually pretty good. Rajshri, I don't know if you have any feedback based on your aggregate understanding of, graduate applications.
So just to add to that, I guess, Bill, is when you're submitting your PhD application, there's a question that asks, your prospective advisor selection 1, 2, and 3. So you would list the people that you want to work with in that questions as well, because when we download the applications, it does get filtered by that, and we absolutely make sure your first, second, and third faculty choices will at least review your application. So you'll belong to the query when they download the application. So that might be another way of getting noticed as well.
And yet still, I would still recommend sending an email and saying
definitely.
I applied.
Mm-hmm.
Yeah, because there is even of those applications, like it can be hard to see who wants to talk with you or who just wants to join, right? And I think that generally it's nice to have a little conversation with someone before we have to start making decisions. And so I would say, if you were to apply sometime in November, the deadline is in December, right? Then reaching out in November and saying, hey, I just applied. that's a good idea.
Definitely, I agree to that. And also, Bill, if you are trying to apply for domestic students, PhD application is waived up until November 15th. So it might actually be an advantage to get your application in by November 15th, even though the deadline is December 15th. Just adding.
Yeah, I saw that. Yeah, I'm just going to give myself, that gives me just enough time to see the projects of those that I'm interested in. So this is going to work out very well.
Cool.
And any more questions for Chris? Okay.
Okay.
I
Well,
think.
yeah, I hope it was somewhat educational and hope I see you all around the halls. I'm here, so I'll look for you.
Thank you so much, Chris, for your time. Really appreciate it.
Thank you. Bye-bye.
Thanks a lot. Bye.